Hi there! Today's lesson is going to be regarding atoms and elements. So, we know that atoms have existed since the very beginning of time, but the ideas regarding the existence of atoms didn't really come about until the early 400 BC, when Leucippus and Democritus proposed the idea that atoms do exist. So these Greek philosophers basically proposed that matter is composed of indestructible particles. They call them atomos. This is Greek word for uncuttable. So they said that matter can't be sliced forever. That you can't cut it indefinitely. That at some point in time you're gonna reach the limit, the smallest part of matter. They also proposed that there are many different kinds of atoms, each different in shape and size, and that they move randomly through empty space. And so these early ideas regarding the existence of atoms were ahead of its time. There were a lot of detractors, right? There were a lot of other Greek philosophers who opposed these early ideas regarding the existence of atoms. Just to name a few, there's Plato and Aristotle. They were against these ideas regarding atoms. So they didn't embrace these atomic ideas. Instead, they believed that matter had no smallest parts, that you can cut it forever and you'll never reach that smallest part of matter, and that different substances were made of earth, fire, air, and water, or a combination of these four elements. And because Plato and Aristotle were more influential at that time, the other people, basically trashed the early atomic ideas. And for millenniums, for thousands of years, they believed that everything was made of earth, fire, air, and water, or a combination of these four. So let's fast forward many centuries later, all the way to the development of the scientific method. So the scientific approach or scientific method basically became the established way to learn about science, to learn about the physical world. You come up with an idea, you test that idea via experiments, and then prove that idea using solid experimental evidence. And so in the early 1800s, John Dalton offered convincing evidence that supported the early atomic ideas first proposed by Democritus and Leucippus. So basically what he did was he summarized other people's work regarding the existence of atoms and published it in his atomic theory. And then other scientists did some experiments that basically supported this atomic theory. And one of these scientists was Albert Einstein himself. And he tried to prove the existence of molecules and atoms via his work regarding Brownian motion. So John Dalton's atomic theory was mostly based off of other scientists' work. He summarized their results in his publication regarding the atomic theory. The theory that all matter is composed of atoms grew out of observations and laws. And there are three important laws that basically supported Dalton's atomic theory. Essentially, they became the foundation of the atomic theory. These are the three important laws that became the foundation of the atomic theory: law of conservation of mass, law of definite proportions, and law of multiple proportions. So first, let's take a look at the law of conservation of mass. So it was Antoine Lavoisier, a French chemist, who first formulated the law of conservation of mass. He basically stated that in a chemical reaction, matter is neither created nor destroyed. So in other words, mass is conserved. So in a chemical reaction, the total mass before the reaction should equal the total mass after the chemical reaction. And so this law is basically consistent with the idea that matter is composed of small indestructible particles. Let's consider this chemical reaction equation here, where you're reacting solid sodium with chlorine gas, and this forms table salt, sodium chloride. So if we started out with 7.7 grams of sodium, and you reacted this with 11.9 grams of chlorine gas, then you would get a total of 19.6 grams of sodium chloride, assuming that this chemical reaction goes 100%. The second law that contributed to the development of the atomic theory is the law of definite proportions, and this is also known as the law of constant composition. Joseph Proust, a French chemist, devoted a lot of his time making observations on the compositions of different compounds, and he summarized his work in this statement: all samples of a given compound, regardless of their source or how they were prepared, have the same proportions by mass of their constituent elements. So let's say, for example, water. We know that water is composed of two different elements, hydrogen and oxygen. So what Joseph Proust is saying is that regardless of where you obtain that water from, whether it's tap water or water from the ocean, from the lake, the river, the proportion by mass, okay, between the hydrogen and oxygen will remain constant, meaning the same. Okay, so let's look at an example here. The decomposition of 18 grams of water results in 16 grams of oxygen and 2 grams of hydrogen, or an oxygen to hydrogen mass ratio of 8:1. Okay, so when you take the ratio between oxygen and hydrogen in terms of mass, you get 8:1. So it's 8 parts oxygen per 1 part hydrogen. And again, it doesn't matter where you get that water from. You take water from tap, water from the ocean, and you analyze it, and you'll always get the same ratio, 8:1. Let's look at another example here. 2 samples of carbon dioxide are decomposed into their constituent elements. So we have sample 1 and sample 2. Sample 1 contains 25.6 grams of oxygen and 9.6 grams of carbon, whereas in sample 2 we have 21.6 grams of oxygen and 8.10 grams of carbon. Show that these 2 samples are consistent with the law of definite proportions. So how do we prove that these 2 samples are consistent with this law? Well, according to Joseph Proust, all you have to do is take the ratio in terms of mass between the 2 elements. So divide 25.6 by 9.6 for sample 1, and if the ratio that we get from there is the same as the ratio for sample 2, then it is consistent with the law of definite proportions. So again, if the mass ratios of the elements are equal for both samples, then they are consistent. So for sample number 1, let's look at the mass ratio by dividing the 2 numbers. So 25.6 divided by 9.6 gives us 2.67 as the mass ratio. For sample number 2, do the same thing, and they're exact same mass ratio. So this proves that the numbers are consistent with the law of definite proportions. So the third law that supported the atomic theory is the law of multiple proportions, and it was John Dalton who contributed the most regarding this law, and he summarized it in this statement: when 2 elements, say X and Y, form 2 different compounds, the masses of element Y that combine with 1 gram of element X can be expressed as a ratio of small whole numbers. So what John Dalton is saying is that an atom of X will always combine with either 1, 2, 3, or more atoms of Y, and they can always be expressed as a ratio of small whole numbers. So for example, you can have XY or XY2, XY3, etc. So let's look at an example here. let's say that we have two different compounds. Okay, so we have two different compounds made of same elements. Okay, and the two elements are carbon and oxygen. So we have, let's say, the first compound here is carbon monoxide, and the second compound is carbon dioxide. And we're given the mass ratio of the two elements in both compounds. So the mass ratio is 2.67 to 1 ratio, right? So you have 2.67 oxygen and 1 carbon, which also tells us that for every 2.67 grams of oxygen, it combines with 1 gram of carbon. And for the second compound here, we have carbon dioxide, and the mass ratio is different. It's 1.33 to 1, okay, which also tells us that for every 1 gram of carbon, we have 1.33 grams of oxygen. So the question here is, are these numbers consistent with the third law of multiple proportions? So what Dalton is saying is that when you take the ratio of the two ratios, you should get a whole number. Okay, so when you summarize this statement right here made by Dalton, he's essentially saying that when you take the ratio of the two ratios, you should get a whole number. Okay, so you always divide the higher number by the lower number. And that's what we're going to do here. We're going to divide 2.67 grams of oxygen per 1.33 gram of oxygen coming from the second compound. So if the ratio of the two given ratios is a whole number, then it is consistent. So we have 2.67 divided by 1.33, and this gives us a whole number. And this basically concludes that these numbers are consistent with the law of multiple proportions. So this leads us to John Dalton and his atomic theory. And his atomic theory can be summarized into 4 postulates. Okay, and so we're going to list all 4 postulates here, but just FYI that some of these postulates are considered partially invalid today, and we're going to explain why. So the first postulate states that each element is composed of indestructible atoms. Okay, so this first one right here is partially invalid because we know today that atoms can be destroyed, right? They're not exactly indestructible. You can split an atom, and that's what atomic bomb is. The second postulate states that all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. So this is also partially invalid because we know that not all atoms of the same element is the same. Okay, they're not the same exactly because of the presence of what they call isotopes, and we're going to talk about isotopes later on. And the third postulate states that atoms combine in simple whole number ratios to form compounds. And the last one, atoms of one element cannot change into atoms of another element. Okay, otherwise that would be alchemy, and alchemy doesn't exist. In a chemical reaction, atoms only change the way that they are bound together with other atoms. So that basically summarizes Dalton's atomic theory. So when Dalton published his work regarding the atomic theory, a lot of the scientists, like physicists and chemists, jumped into the field because they want to learn more about these atoms, what they're made of, and what they look like. Okay, and so we know today that atoms are composed of subatomic particles, and the first one that was discovered is the electron. So J.J. Thomson was a research professor from Cambridge University, and he did extensive work regarding cathode ray tubes. And he's actually the guy who discovered the electron. So when you go to a gas station, you see these neon lights, right? Neon lamps or neon signs. That's basically what cathode ray tubes are. So when you look here at the bottom right corner, you see this. This is basically the device, the cathode ray tube device. that J.J. Thomson came up with. So you have this glass tube right here, which is filled with an inert gas. Okay, so it could be a neon gas, could be argon gas, helium, any of the noble gases or inert gases. And then he capped it with electrodes and hooked it up to a electrical source. And he basically discovered that when you run electrical energy or electricity, a beam of particles traveled from the negative electrode, known as the cathode, to the positive electrode, known as the anode. He also found that these particles, these cathode rays, travel in straight lines. They are independent of the composition of the material used, and that they carry a negative charge because of the fact that these particles traveled from the negative electrode to the positive electrode. Thomson performed several more experiments by measuring the charge to mass ratio of the particles, which he determined as negative 1.76 times 10 to the 8th power coulombs per gram. And that's when Thomson basically discovered the electron, which is a negatively charged particle present in all atoms. And in 1906, Thomson received the Nobel Prize in Physics. When Thomson published his work regarding the charge to mass ratio, a lot of the scientists wanted to know what the charge is of a single electron, as well as the mass of a single electron, because Thomson didn't know what those numbers were. He only knew the ratio, the charge to mass ratio. And so Robert Millikan was the physicist that successfully determined those two numbers, the charge of the electron and the mass of the electron. And so he did this experiment regarding, or later became known as the oil drop experiment. So Robert Millikan performed this oil drop experiment using this device shown here. So he created this chamber containing two charged metal plates that allowed him to control the movement of this oil drop shown here. He could halt the movement. He could even reverse the free fall if he wanted to. But what he did was he just halted the movement of this oil drop so that that oil drop is at a fixed location, so that he can see it and study it. So this chamber here is equipped with several accessories, like for example, a viewing microscope and a light source so that he can see what he's looking at, an ionizing radiation source that rendered the oil drop a negative charge, and an atomizer that basically squirts oil into the chamber that then passes through a single slit, little hole here, that only allowed a single oil drop to pass through. So he looked at hundreds of droplets, maybe even thousands, and used statistical analysis to determine the charge of the electron. And so according to his analysis, the measured charge on any drop was always a whole number multiple of negative 1.60 times 10 to the negative 19, which is essentially the charge of a single electron. So then he used this information along with Thomson's charge to mass ratio to determine the mass of a single electron. So all you have to do is multiply the charge of a single electron by the mass to charge ratio in order to get the mass of a single electron. And so using these numbers, he was able to calculate the mass of a single electron, which is 9.10 times 10 to the negative 28 gram. So it's very lightweight. So going back to J.J. Thomson, if you remember, Thomson is the one who discovered the electron, and so he did a lot of studies regarding atoms and electrons. And he had an idea of what an atom might look like structurally. And so he proposed that the negatively charged electrons were small particles held within a positively charged sphere. And he called this model the plum pudding model. And plum pudding is basically a British dessert. And then J.J. Thomson, again from Cambridge University, he had a student, a PhD student at the time, Ernest Rutherford, and he asked Rutherford to confirm whether this is true, right? So again, he had a hypothesis that of what an atom looks like. And so, like any hypothesis, you got to prove it experimentally and support it with solid evidence, solid physical evidence. And so Rutherford tried to confirm Thomson's model using this or via this experiment called the gold foil experiment. So what exactly is this experiment that Rutherford performed to confirm Thomson's hypothesis or Thomson's plum pudding model? Well, this gold foil experiment, or in this experiment, Rutherford directed positively charged alpha particles at an ultra-thin sheet of gold foil. And the idea behind this experiment is that if the plum pudding is correct, then these alpha particles that were directed through the gold foil will pass through the foil, because these alpha particles are a lot heavier in comparison to electrons. So this is how they designed the gold foil experiment. They had a source of alpha particles that were basically directed at a gold foil, and then this gold foil is surrounded by detectors that can detect alpha particles. So the mass of an alpha particle is similar to the mass of a single atom of helium, and helium is 4 times heavier compared to a hydrogen atom. And a hydrogen atom contains 1 proton and 1 electron, and the mass of an electron is 2,000 times lighter compared to the mass of a proton. So you can imagine an alpha particle shooting at an electron, right? So if the plum pudding model is correct, you're basically saying that this gold foil is composed of a bunch of electrons surrounded by positive charge. And so if the plum pudding model is correct and you shoot an alpha particle at a gold foil, then these alpha particles should be able to just pass through the gold foil. It's like saying, throwing a baseball in the air, right? And the air molecules would not affect the trajectory of that ball. So they shot a bunch of alpha particles at this gold foil, and the result of this experiment took everyone by surprise. Most of the alpha particles passed through with little or no deflection. Some of the alpha particles were deflected at smaller angles, while some at even larger angles. So that suggested that these alpha particles hit something extremely heavy, something massive. It's like that baseball hitting a wall and it bounced right back. So Rutherford concluded that the plum pudding model was incomplete. Something else was missing, something massive. So again, the result of the gold foil experiment was completely unexpected, because the majority of the particles passed through the foil, while some were deflected and others bounced back. And so Rutherford came up with a new model of the atom, and he called it the nuclear model. So this summarizes Rutherford's nuclear model. So he said that most of the atom's mass and all of its positive charge are contained within the nucleus, which is located in the center of the atom. And most of the atom's volume is basically empty space throughout which tiny negatively charged electrons are dispersed. And finally, the number of electrons outside of the nucleus equals the number of protons, which basically makes the atom electrically neutral. And protons are the positively charged subatomic particles. Although Rutherford's model was successful, especially in disproving the plum pudding model, it was still considered incomplete because it couldn't explain why helium is 4 times heavier compared to a hydrogen. A helium atom contains 2 protons, whereas a hydrogen atom contains 1 proton. And so why is it that a helium atom is 4 times heavier compared to a hydrogen? And so something else was missing, and that's basically the neutrons. So about 10 to 15 years later, James Chadwick discovered the neutrons. And the neutrons are the neutral subatomic particles. They don't have any charge, unlike electrons and the protons. Protons are positively charged, electrons are negatively charged, the neutrons are uncharged. And it was James Chadwick who discovered them. And this is Jimmy Neutron from the show. A neutron's mass is similar to a proton's, and so a neutron is technically a lot heavier compared to an electron, similar to a proton. So these are their relative masses. So proton's mass is 1.673 times 10 to the negative 27 kilogram, whereas a neutron has a mass of 1.675 times 10 to the negative 27 kilogram. And so helium is 4 times heavier than hydrogen because it contains 2 protons and 2 neutrons, whereas a hydrogen atom contains only a single proton and an electron, but with no neutron. So this table right here summarizes the relationship between the 3 different subatomic particles in terms of their mass and relative charge. So again, these right here are the actual charge of the subatomic particles, but relatively speaking, we can simplify that into just +1 for proton, 0 for neutron, and -1 for electron.